Welcome, everybody. Thank you for joining our seminar today. I'm happy to introduce our speaker, Barbara Giunti, and she'll be speaking about invariants for tame parametrized chain complexes. Thanks, Barbara.
Okay, thank you, Henry, and thank you, Sarah, for giving me the opportunity to present our work. This is a joint work with Wojciech Chachólski, who gave actually a first part of the seminar last week, and Claudia Landi. Okay, so let's start. Okay, yes, it's working. So I'm assuming that many of you are pretty familiar with this pipeline, which is quite standard in persistent homology. So usually what we do when we work with persistent is that we start with data, we convert it into parametrized chain complex, we apply homology, and then we retrieve persistent modules in any degree, and we decompose it, finding invariants, and then retrieving information. So as an example, here there is a Vietoris-Ript complex of 6 point, and here this persistent diagram in dimension in degree 0. Okay, so our project was mainly about skipping the step in the middle. So one of the reasons why is that parametrized chain complex provide a nice universe where to study different objects that usually are handled separately, like, for example, commutative ladders or zigzag modules. So the idea that we have, or the aim of our work in this talk also, is to convince you that we can find computable invariants for tame parametrized chain complex. So the method that we use it as we refer to a homotopy method, specifically mode category. So I'm going to introduce immediately this most technical part of the talk, which is going to be the definition of the mode category and some structure in it. If you are not familiar with mode category, do not worry. I'm going to explain you when we need it and what we need it. So a mode category is a category where we choose 3 different classes of morphisms. First one, call it weak equivalence, that we identify with this tilde, then fibrations with the double head arrow, and cofibration with a hooked one. So we require this category and these classes of object to satisfy 5 axioms. So the first one is that all small limit and colimit exist. So what it means basically, so hands in, it means that I'm sure all the push out, all the pullback, all the product and co-product exist in my category. So I'm comfortable with constructing many of the operation that we usually want to have. For example, the initial object, which is actually a colimit, we are sure that this exists in any mode category, and this is very important because we use the initial object to define the cofibrant object, which are going to be crucial in this talk. So a cofibrant object in a mode category is an object for which his morphism from the initial object, that once more we know it exists for this axiom, is a cofibration. Okay, so the reason why we want to study that is usually they are more manageable, or in some categories, mode category, they are more manageable and simpler than a general object. Okay, let's move on the axioms. So then we ask the weak equivalences to have the 2 out of 3 property, which means that once we have 2 morphisms with their composition, if any 2 of these 3 morphisms is a weak equivalence, then so is the third. Then we ask each classes to be stable under retract. And since I'm not going to use it, this axiom, I'm just going to skip it. So if you know it, very good. Otherwise, don't get distracted. Axiom 4 is quite useful because it's actually telling us something about these choices. So what it's telling me, what this axiom is telling me is that what I want to have is anytime I have a cofibration, which is also a weak equivalence fitting in this diagram, then it has the left lifting property with respect to fibrations. Okay, and vice versa. And also, so at the same time, I want to have both. Anytime I have a fibration, which is also a weak equivalence, it has to have the right lifting property. So what it's telling me is that once I choose, for example, weak equivalences and fibration, I'm forced on the choice of cofibration to have this lifting property. Okay, so we will see that later. The most important axiom, I'm going to talk over and over about this one, is the factorization. So what we want to be sure is that once we have a morphism between two objects in the model category, then we can factorize it as a cofibration, which is also a weak equivalence, and then a fibration, or actually at the same, and we also want to have a factorization in which I have first a cofibration and then a fibration weak equivalence. Now, notice that I'm asking existence. I'm not asking anything else. So I'm not asking functoriality, any sort of naturality for these maps. I'm not saying that I want an explicit construction, neither for the lift nor for the factorization. So basically the problem when we want to turn model category, so we want to make model category talk with a computer, is that usually computers do not react well when you just say that something exists. Computer wants to know exactly how to construct. Okay, so we have a priori many possible factorization, and they are not isomorphic one to the other. But we want to make some choice. So we want to have some factorization which is nicer in some sense. So we take a morphism, we factorize it using this fifth axiom into a cofibration and then a fibration. Okay, and then we say that this factorization is minimal if any endomorphism from the factorized, so the object through which we factorize, is actually an isomorphism. So the reason why we choose this minimal factorization is that this provides some invariant, sort of, in the sense that minimal factorization are unique up to isomorphism. So there is, if I have a minimal factorization, I can talk about the minimal factorization. The problem is, in general, they do not exist. So I have to, once I have my model category, I know for sure that I have one factorization, but I need to work to show that there exists a minimal one. Okay. Now, the reason why we are so interested in minimal factorization is also because they provide us a nice invariant, which is this called minimal cover. So again, let me take the initial object, which I know it exists in any model category for the first axiom, and let me take a minimal factorization of this map, okay? Then I call it a minimal cover. Now we know that this minimal cover is an invariant, so is unique up to isomorphism. And since we're gonna talk about over and over this minimal cover, let me state more clearly what it does. So it is an object, so actually it is a morphism, from an object which is cofibrant because it's receiving a cofibration from the initial object, okay, in here. And such that the map over my object is both a fibration and a weak equivalence. So what I'm saying is that once I decided what are my fibration and weak equivalence, I know what kind of information they are retaining. And the minimal cover is a nicer object in the sense that it's cofibrant and thus maybe simpler, that retain this information carried by the weak equivalence and the fibration. And then I have the minimality condition. So I want to have that any morphism in this that makes this triangle commute is actually an isomorph. As before, the minimal cover, since it's a minimal factorization, need not to exist. So we may miss that.
Barbara,
Okay. Yes.
Could I ask a question on the prior slide about minimal
Absolutely.
factorizations? Back one. Oh, there we go. So G is our morphism from X to Y, and
yeah, which is not depicted here. It would go from here to here. Yeah.
Right. But it factors as beta composed with alpha.
Yes.
And then when you say the factorization is minimal, you're talking about the factorization of beta composed with alpha.
And alpha, yeah.
Okay, so it's minimal if whenever you have I see.
So those are two copies of the same factorization.
Down below, okay.
Exactly. And then I'm asking that anytime, so to pass from one to the other, I cannot forget anything. I cannot gain any information. So to move, if I have an endomorphism, I have an isomorphism.
I see. I see.
The only way I can pass from the factorization to itself is retaining all the information.
And it's sort of saying y prime is no larger than it needs to be. Is that right?
Exactly, exactly. That's why it's minimal. Very good.
And then Wen has a follow-up question, now moving to covers, a particular case. Wen wanted a reminder what the definition of a cover is.
Here?
Yeah.
Okay.
So she chatted in, what's the definition of a cover again?
Oh, it's here. So it's a cover, not a minimal cover. I guess this is a question. Because here I have a minimal cover.
I'm not sure. Maybe she's asking what's the definition of a minimal cover, since.
Okay, so the definition of a minimal cover, the definition is here. So is the minimal factorization of the morphism from the initial object to X. So the minimal cover of X is the factorization of the morphism from the initial object to X. And if we want to unpack this definition, it means that it is a morphism, okay, such that the domain is cofibrant and the morphism is a fibration and weak equivalence. And then we have this minimality condition, so that any time I move, then I have an isomorphism.
Thanks.
Okay.
Hold on. So I mean, what's your definition of your source of the morphism beta? So cover X.
Yes, is an object. Is the object that created the minimal cover. So the minimal cover is actually a morphism. So to specify, I know for sure it has to end on X, but to specify the morphism, I need to specify both the domain and actually the map.
Yes.
So
okay.
The minimal cover is the morphism and thus also the domain of it.
Okay, thanks.
Okay, good. So yes, please interrupt anytime because I tend to go very quickly. So, okay. So now I finished with all the introduction about general model category. So we can start talking about something more concrete, not too much, but a little bit. So chain complexes over a field. We're talking about the category of non-negative chain complexes. Is there another question? Okay. I saw the chat blinking.
Yeah, so Leonid asks, is it possible to give an example of a minimal cover, for example?
Yes, can I give the example once I introduce all the objects?
Yes, exactly. I suspect you're getting there.
We're gonna have, so the first part of this talk is gonna be a little more theoretical, but then you're gonna have a lot of examples. I promise that. So keep till the end. There is this beautiful paper from Dwyer and Spaninsky where they describe a model category on CH. Actually, they describe it on a general, so for general chain complexes, we reduce ourselves just for the ones over a field. So a model category means that I need to show you what are the weak equivalence, fibration, and cofibration. So weak equivalences are the isomorphisms in homology. The fibration are the epimorphisms in positive degree. So I'm asking nothing on degree 0, okay? Just to have a chain map, but nothing else. And cofibration are the monomorphisms in each degree. Also, actually, I have an example right here. Because in this category, the initial object is the chain complex, which is 0 in all degree, okay? And obviously, any object, so any chain complex get a monomorphism from 0, okay? So it means that every object is cofibrant, which means that in the category of chain complexes over a field, every object is its own minimal cover. Because since every object is cofibrant, this map here is a cofibration. And then the identity is in particular an isomorphism in homology, and of course an epimorphism in positive degree. Okay. Even too much for that. Okay. Now, let's see what we can construct once we have these nice chain complexes. Quite a lot. So given a chain complex X, I want to define 3 other chain complexes of X. So as given in any degree is given by the cycles of X. And I can write it as a direct sum because it has a zero differential. Okay, so all the differential are zero. I can do basically the same with the boundary. So I defined the boundary chain complex. Again, it has all zero differential, and it is the boundary of X in any degree. And then I can use it to the two of them to define the homology of X. So the direct sum of the homology in each degree. Okay, all the three of them have zero differential, and this is quite important. Then we can also define a cone. So all of these are standard construction, but I wanted to recall them here. The cone of a chain complex is a chain complex given by in degree n+1 is the chain complex itself in degree n+1, but also the chain complex, so the direct sum with the degree n of the chain complex. And the boundary map is the boundary map of the chain complex with a minus to ensure that the composition is zero, and the identity. So xn is actually mapping on this xn here with the identity. And this is important because what I have is that any chain complex has trivial homology. Okay. Yes, the cone of every chain complex has trivial homology. Okay. Now, since we are working with chain complexes over a field, every chain complex has actually a nice decomposition. So I'm not going to show you exactly how to reach this conclusion. I will ask you to trust me. But the point is that every chain complex can be written as the sum of its homological part plus the cone of its boundary. Okay. Now, the reason why this is interesting is because we can use this decomposition and this construction to something that we are interested in. For example, to define the minimal factorization of chain complexes. So actually, the minimal factorization exists, and we can construct it explicitly. So let's see what is the reasoning behind the construction of it. Okay. So the first idea is to say, okay, let's play safe. Let's start with a factorization in which I'm taking X, I'm including into the cone, so in each degree, simply. And then I'm mapping with G over, so the map that I want to factorize over this other direct summon. And then I'm mapping here with what is an epimorphism, because Y goes over Y. And since the homology of the cone is zero, this map is also weak equivalence. So we have a factorization. It is a cofibration and a fibration weak equivalence. It's not minimal. That's because there are too many elements in this cone. So it's too much. We need to restrict it. So one idea, the idea that we had is that, okay, let's start not with the whole X. Let's consider just the kernel of this morphism, okay? Now, let's take, again, we want to have something here with zero homology. So let's take the cone of the kernel, okay? It turns out this thing is still too big. It's not a minimal factorization. And the reason is that if you look at the decomposition that I just showed you, we know that since the kernel is in particular a chain complex, it is the direct sum of something which already has trivial homology plus something that does not have it, okay? So maybe taking the cone of all of it, it was too much. But if we make sure that just this part is as a trivial homology, then it is enough. And it turned out it to be. So we can, for appropriate phi, which we describe more in detail in the paper, this is the minimal factorization of a chain map. So what we have is that if you give me a chain map, I have a way which is almost algorithmic because there is something that we still need to implement to compute the chain map, okay? So this is interesting. Okay, now we can finally talk about tame parametrized chain complexes. So, okay, a tame parametrized chain complex is a functor from the non-negative real into the category of chain complexes. It is a functor, yes. Okay. So the point is here, if I'm working with data, is that this thing is too big. I can have uncountably many changes. This is definitely something that is not going to happen on data. Okay, so let's restrict ourselves to something a little simpler. And so we consider a discretizing sequence, which is an increasing sequence of non-negative reals, such that the transition morphism of X could fail to be an isomorphism only if it's passing by one of the elements of the sequence. So I'm saying that, yes, I have a chain complex for every non-negative real numbers, but actually the only one that change are finitely many, okay? And we call it a chain complex tame if it emits one discretizing sequence. So let's look at some diagram, because I think it's useful. This is a general tame parametrized chain complex. So horizontally, you can see the step of the parametrization, and vertically, you can see that for every time we have a chain complex. So what we have is that this composition is 0, okay? And in this arrow, basically nothing is happening. The only moment when something happening is from here to the new, to something after the next, the element of the discretizing sequence. Now remember that what we wanted to do is find invariants, computable invariants. Now the bad news is that we cannot rely on the composition, because in general, there are infinitely many types of indecomposable. So we cannot really teach a computer to recognize them. So okay, we spent quite some time talking about model categories and cofibrant objects. So let's see if they can be useful. Okay, but before I go into the details, okay, I want to reward you with some examples. Okay, so why do we want to study tame parametrized chain complexes? Well, first of all, because if you give me a persistent module, then I can think about it as a tame parametrized chain complex. I'm simply putting it in degree 0, and I'm simply putting 0 everywhere else. Maybe not so interesting one, but it's still exactly a tame parametrized chain complex. Same things, and this is more interesting when we are talking about commutative ladders. And it's more interesting because usually these two objects do not really talk with each other, but now they are just example of the same universe, okay? So it's non-zero only in degrees 0 and 1, and 0 in everywhere else, okay? Now, another example is the zigzag modules. So it's a bit more difficult, but let me take a zigzag module, so something like this. And let me show that we can actually embed it into a tame parametrized chain complex. So the way we do that is we take the forward map, okay, of the zigzag module, and we consider that as a transition morphism. Basically exactly how it is. And then we take a backward map, and we consider that as a boundary in here. And I put this square to show you that actually it's not just the boundary here, it's the boundary for all this interval, because I have a discretizing sequence here. So I'm not allowing any change in between the two elements in here, okay? So, and again, at the end of it, then I'm gonna put 0, so just for the, at the time tau 2, and then I'm gonna move on with my next forward map, and then I'm gonna put the boundary back. I'm just jumping up in degree from one to the other. Okay? Any question? Okay, then we are ready to define a model category over the tame parametrized chain complexes. So again, we need to define, we need to choose some classes of morphisms. So we start saying that the weak equivalences are the morphism. So a morphism is a weak equivalence if it's pointwise a weak equivalence in CH. So if for every T, H, the F of GT is an isomorphism of, yes. Is a fibration if it's pointwise an epimorphism in positive degrees. Okay, and again, this means that it is a fibration in CH. Okay. Now, as I told you at the beginning, now axiom, the fourth axiom is forcing me. I have this straightforward definition, and the definition of cofibration, I need to have the one ensuring the lifting property. So I have this one. So I have a morphism is a cofibration if it is a monomorphism, okay, at the step 0. And then I'm not really asking pointwise monomorphism, this will not be enough, but I'm asking that the mediating morphism of this push out, it is a monomorphism. So let me explain a little better. I'm taking any two element in the poset. I'm taking the push out of the transition morphism between the two of them and the map that I want to check it is a cofibration. Okay, so this push out, it exists because those are all chain complexes. Okay, so we are sure it exists. And then since both xt and ys are mapping to yt, this with the map G and this is with the transition morphism, then it means that there is one unique morphism from the push out to yt. Now, what I'm interested in to be sure that this morphism here is a monomorphism. Okay, so it's a little trickier, but this was the technicality of it. Okay, and with these choices, we have that tame is a model category. Okay. Okay. So now there is one construction. So I hope you will like it. So I'm not going to show you the proof of the axioms because those are quite technical. I don't think they are so interesting for this venue. But what I wanted to show you is that there is a straightforward way, so not a straightforward, but a constructive way, an explicit way to construct the minimal cover. And this is very interesting because then we wanted to implement that. So we want to be sure that we can do it. But before going there, what I wanted to point out is that constructing the minimal cover means constructing the minimal factorization of a very specific morphism. Okay, so the method that I'm going to show you, the idea, is actually giving you the minimal factorization of any morphism. Okay, we are just taking advantage to know what is that domain. The domain is 0. Okay, but the method is the same. So, and then we can also use it is the same idea that we can use to show axiom 5 in this category. Okay. Okay, so let's go on it. We take an object, okay, and the morphism from the 0 object, and we want to find its minimal cover, so its minimal factorization. Let's start along the discretizing sequence. So let's build it step by step. Step 0, I have a chain complex. And a chain complex are nice because all the objects are cofibrant and we have the minimal factorization, which is actually the identity. So the first step is easy. We just need to take the chain complex itself. Then we need to go further. So to go further, we take a look at the transition morphism in X and in 0. And then we focus on these two, one here, the one that are now in red. Now we want to take the push out of it. To explain to a computer how to do the push out, it may not be so straightforward, but in this case, this is the identity, which means that this push out is actually the chain complex X tau 0 itself. Okay, so it's easy, it's implementable. Now remember, we spent some time talking about the minimal factorization of a chain map, which is something that we have here, where this is this will be the mediating morphism of this push out, but is actually just this transition morphism here. Okay, so we can take the minimal factorization of it. Okay, and this minimal factorization that we know it exists because I showed you the construction before is actually the second step for the construction of the minimal cover. So at the step 0, we have the chain complex itself. At step 1, we have this. Okay, so when we go to the ith step, we can assume that we constructed everything before, okay? And what we do is we do the same. So we take the transition morphism, we take the push out, that in this case is again the same object here. And this time, this is the mediating morphism, but is actually the composition of this morphism here that came from the previous minimal factorization and the transition morphism. We take the minimal factorization of it, and we have it. So we have it for step I, we have it for step I plus 1. So what we have is that we have an explicit construction for minimal cover. And as I told you, it is an explicit construction also for minimal factorization, and this leads to the fact that we don't just have the minimal cover, that the minimal cover exists in tame, but we have that minimal cover exists for any multi-parameterization, okay? So there is, in this implication, there is a little bit more, but we can have it. Now, I took quite some time to describe how to construct the minimal cover and that any object emit a minimal cover. That is all amazing, but what can we do with them, right? So if I cannot extract invariant from a minimal cover, that would be pointless, but we can, of course. So first, let me characterize what is a cofibrant object, okay? Because all the minimal covers are cofibrant. So a cofibrant object in tame is a tame parametrized chain complex whose transition morphisms are all monomorphisms. So I'm assuming that you may be more familiar if I say that with the name, if I say that a cofibrant object is a filtered chain complex. Okay, so those are exactly the same, two names for the same thing. Now, why they are so beautiful? That's because despite the fact that in general we cannot describe all the indecomposable cofibrant objects are fully described, okay? So if you give me a cofibrant object, I can uniquely decompose into interval spheres. So now I just have to tell you what is an interval sphere. And this is one of the last definitions, then we're gonna have just examples, okay? So an interval sphere is a tame parametrized chain complex given me by 3 numbers. So I have a non-negative integers, a starting point, okay, and an ending point, okay. So it's a tame parametrized chain complex which is 0 before the starting point. Between the starting point and the ending point is given by the sphere in degree n. So it's a chain complex which is 0 everywhere, but in degree n, where it is at the field on which we are working on. And then it becomes a disk. So a chain complex which is non-zero only in degree n plus 1 and n, where it is equal to the field with the identity in between. Okay, so now let me put some picture because I think it's useful. So a chain complex is, interval spheres can be depicted as simply a point on a persistent diagram. So this is the starting point and this is the ending point, okay? Yep.
Barbara, Mikael Vejdamo-Johansson asked a question. Is this mimicking reduced homology?
Yes, yes.
And then can I ask a question? So
yeah.
You have this filtration here, which is, you know, the empty set and then a sphere and then a disk.
Oh,
so
yeah,
if I had a different filtration, which was the empty set and then a 2 torus, and then maybe a contractible, you know, it fills into a solid 3-dimensional ball, how would that decompose? So is this sort of a decomposition up to homology? Does it decompose as like
no, wait, sorry, I don't. So if you have, so you have a cofibrant object, right?
Uh-huh.
Okay, so all the maps are monomorphism,
right.
And then there will be some of this object here. So
right.
These interval spheres. So yes, basically what happened is that this part is taking care of homology, okay? And this part is taking care of the contractibility of it.
So for the example of like the empty set, including into the 2 torus, including into a filled in 3 ball, I mean, does that decompose into like 2 circle intervals and 1 2-sphere interval, and meaning that?
No, that I think that in this case, what you will have is that, so one of them, because, okay, what is happening here is that here you have a circle that gets filled by a disk.
Right.
Okay, so if in your 2 torus you have this disk that circles that then get filled, so each of them will be 1 interval sphere.
Okay, okay, thanks.
Okay.
Yeah.
So, okay, this is a persistent diagram, a point on a persistent diagram. But then let's take a look at the fact that the ending point can be equal to S or equal to infinity. So in the case is equal to infinity, it means that I have just one infinite homological class, basically. Okay, so I have a circle that never gets filled. Okay, but I can have something also that start immediately as a contractible object. Okay, so immediately as a disk, and then it will lie on the diagonal. And those objects are actually quite important in the decomposition. And so then I want to show you the same example that Wojciech showed you last week about why points on the diagonal are actually, so we cannot really disregard them totally. So let's take 9 points, okay, where in one set, they are distributed along a line, and in the other one, they are along a grid, so over a grid, okay? Now, the metric of them is that the balls, so I'm taking a filtration, so I'm letting the ball grow, but the balls are actually squared. So I have little squares growing. Okay, now as you can see here in both cases, I have 9 connected components, and then at a certain point they touch each other, and it's just one blob in both cases. So this is a filtration, and so I can, a cofibrant object, I can decompose it, and I will obtain two persistence diagram. And in this case, this is the decomposition in degree 0, okay? And you can see that there is absolutely no difference. In the same way as if I'm taking the persistent module of dimension 0 of these two filtered chain complexes, I will see no difference. And so as you can see, there are no hidden cycles. So if I'm taking the persistent module in degree 1, I will see no difference again because it's just trivial. But when I'm decomposing them as a filtered chain complex, I'm getting something on the diagonal. And something, I mean, this point added actually multiplicity 12. So it's not really, we can really disregard it. And if we take even bigger disk, okay, so if we make our square grow a little bit, then we have something else in here, but here we have 28 disk, so 28 interval sphere in this point. So this is carry on some information. I use it also, yes, I haven't said, I use the square to denote the interval sphere of degree 1. Okay. Okay. So now let's move on to other examples. Yeah. Okay, so I wanted to show you how we can recover some information that we are familiar with, also with this new method that we are being showing. So here, let's take the Aviatoris filtration of 6 points. And this time the balls are actually balls. Fine, okay? So I can consider the parametrized persistent module H0. Okay, now I didn't want to put the metrics here because they're going to be big, but you can see immediately that this cannot be a monomorphism. So this is not a cofibrant object, okay? But then we can construct the minimal cover of it, okay? Which is something like this for the appropriate maps. And then we can decompose it, okay? So let's go back to the picture because then we can actually understand what is going on. So here we are exactly what we would expect from persistent homology, right? So we have something, so here we have 6 connected components and 2 of them merge at this step. And here we have an interval sphere that starts in 0 and then here. So 2 of them actually. And then we have another one with merge here. So we are retrieving the same information in this case. But what if you don't want just to study H0 of this filtration, but you wanted to compare with something which has less density, okay? So with something, a lower density. Then in this case, what you will obtain is a commutative ladder comparing H0. And again, I decided not to write these huge matrices, but those are clearly not monomorphisms, okay? So then, trust me, we can compute the minimal cover, okay, of it, and we can decompose it. And yeah, trust me again, this is the decomposition. But what I wanted to show you is what is the information that this decomposition is carrying out of the picture, because I think it's interesting. So let's take a look what we have here. So here we have 3 connected component, and here we have 6 connected component, okay? So it's like there are 3 connected components that are both here and here. And actually here we have an interval sphere in degree 0, so 3 interval sphere, both, all of them starting in 0, okay? But then we have another 3 interval sphere in degree 0, okay, that are lasting for a little longer. And actually each of them it is telling us that there is 1 connected component here, which is not up here, okay? And as a matter of fact, here I have 3 connected component, and here I have just 4. So it's this one that is persisting until this step, okay? But then I have something more. I actually have this square, so this degree 1 interval spheres that is telling me that at a certain point, so a step 085, okay, up, so in this higher dimension, in this lower density set, I have 1 connected component more than what I have down here, okay? And these things, so here I have 3, here I have 2, 2 and 1, and then they get the same number only here. And what I have is an interval sphere that is telling me exactly this. Okay, so we need to find the interpretation. So we need to work to understand exactly what is the information that this new persistent diagram is telling us. But there is some information that is able to capture. And we can do it using the minimal cover, but we couldn't really analyze using standard method, or as far as I know.
So okay. When you had more connected components up above, that appears as a 1-dimensional homology
exactly.
thing, as
when I
have
a
0-dimensional. Yeah.
More connected component down here, it appears as a lower, a lower degree interval sphere. So it is carrying some information. It was worth studying. Okay. So let me summarize what is minimal cover, some property of the minimal cover. So when we are working with persistent module, the minimal cover is a complete invariant, and is actually recovering the same information as the barcode. So there is a perfect matching between what we already had. It's nice. The minimal cover, unfortunately, is not a complete invariant for commutative ladders. And this because basically the minimal cover is very good in remembering or noticing when things start, either constructible things or homological things, but it's not really good in catching when they end. So for example, here I have a disk, just that stay from here to here, okay? And then I have a disk that stays forever. Okay. And in both cases, the minimal cover is actually this object here. So it is 1. Too bad. And the minimal cover is not a complete invariant either for zigzag modules. And that's because we move up in dimension. So let's take 2 zigzag modules, okay? One with the top matrix and one with the bottom metric. So what we have is that if I look at the top one, I have the decomposition is 1 long bar above all of it and 1 short bar just in the middle. While if I'm looking here, the decomposition is going to be 1 bar from here to here and then 1 bar from here to here. So the bars decomposition is different. But when I move it to tame parametrized chain complex, actually their minimal cover is the same. The reason is once I jump up in degree, I'm no longer able to remember the length of the bar before. Okay, so we need something else to capture all the information in this case. So now, I was a little cheating in the title because the title was Invariants for tame parametrized chain complex, and I was talking extensively about one of them, not multiple. But I wanted to show you many examples and constructions, so I decided to focus in this way. But of course, there are many more. For example, there is the minimal representative. So if you give me an object X, I can find a sequence of weak equivalences, okay, that leads to an object Y, which is cofibrant, and such that any weak equivalence from Y to Y is actually an isomorphism. So this is an object that it discriminates up to weak equivalence, so a little less actually than minimal cover, but it's characterized not to have any points on the diagonal. So for example, if you know for sure that your data are going to have noise on the diagonal, then you may want to study them with a minimal representative. It's going to be easier to compute. Okay. Otherwise, we can take a morphism and we can take his minimal factorization, which is again an invariant. Now the object A that given by the minimal factorization is in general not cofibrant. So I cannot really use it. But the co-kernel of this map, it is cofibrant and is uniquely associated to this morphism. So I can use it as an invariant to retrieve different information about morphism, for example. And there are many more. Oops. Okay. Okay. So now I almost finished. This is the last slide. Okay. So I hope I convinced you that we can study TDA using a new pipeline. So we start with data. We build parametrized chain complex at tame 1. And we use different cofibrant approximations, such as the minimal cover that I presented to you today, to retrieve invariants that can lead to information, possibly new information. Okay. Now, if you want to take a look of more in detail about the construction, we have a paper on arXiv. So you're welcome to go there and then ask us questions. And what I also wanted to point out is the work is not finished. So we need to study the stability of this process. For now, we have some preliminary result about the composition of cofibrant object. So also with points on the diagonal, there is hope. We need some more work and we need to restrict ourselves a little, but it can be done. We need to implement the computation of the invariant. And about that, I want to say that we hope to, we are working on the computation of the composition of cofibrant object, and we hope to come up very soon with a paper. And it's very interesting because it's also explaining some standard optimization of computing persistent homology. So working at chain complex level is really useful also for understanding standard techniques. Then of course, I want to say, so I show you an example that we can carry on new information using these new persistent diagrams. But what exactly does it mean on real data? That we still do not know. And of course, I invite you to define new invariants and to define new different model structure on the tame parametrized chain complexes, because there can be many. So I presented you just one of them. And with that, that's be all. Thank you very much.
Fantastic. So as is sort of a tradition, let's have everybody briefly unmute yourself and let's applaud for Barbara, and then we'll mute ourselves again before questions. So. All right, fantastic.
Actually, before the question, so you can summarize your idea. I wanted to show you something that is a side work of mine and Yanni Lazowskis, who is a postdoc at the Rand Levy Group in Aberdeen. So we are working on a database for real-world application. So let me show you, and I should be able to switch. Let me see. Yes, this one. Okay, so this is how it looked like. And it is an open database. So you just go to group library and you should be redirected here. So this is, okay, it doesn't have so many. For now, we have just 66 papers, but we have some labels. So if you're very curious about real world application of TDA in anthropology, then you can click here and have a list. Okay, not so long for now, but then the good things is that you can automatically export in BBTech or LaTeX or whatever. So it's quite useful. And so if you notice that your paper is missing, please write me. I'm gonna add it as soon as I can. Also, if you notice that you don't like the labels, please, we welcome any improvement that we can do. if you want to collaborate, you just need to subscribe, and then we are gonna add you in. So anyone can read it, but not everyone can edit. So if you want to be part of it, just write us. Okay. So that was it. That was the ad that I wanted to show you.
Thank you. It's a nice compilation of papers and data sets. So questions for Barbara?
Hello.
Yeah, I have a.
Pepin, why don't you go first, and then we'll have, I think, maybe Sarah go next.
Yeah, sure. Yeah, so thanks for your talk. It was very nice. I wrote down some questions, but you actually addressed them somewhat at the end. But I would like to know a bit more maybe about the stability, because you said something like, but do you know, for example, something about stability of the commutative letter case, or?
Not yet, because what we have for now, so what we were studying is, let's have they finite data set, okay, with the same cardinality, just for sort. And then we have some measure between them, so we can say that they are close, these two data set. And then what we will have is that the composition of the two filtered, the two cofibrant objects are going to be interleaved at chain complex level. What we need to add is the part where we actually study the minimal cover. So for now, we don't have an answer for that. We are working on that, and it's very challenging, because we need to talk that we need to think about how to include the points on the diagonal and what is the meaning on the point on the diagonal. So it's a nice change of framework.
Right.
Yeah.
Can I make a comment? Sorry, this is Wojciech.
Yeah, please.
So the biggest obstacle there is that in order to talk about stability, you need to be able to talk about, first of all, metric on parametrized chain complexes. So we have certain examples, and for these basic examples, we have stability. But generically, one needs to come up with a way of producing metrics or parametrized chain complexes. Okay. And if you give me a metric, you might then ask, is this process stable? For example, when the initial metric spaces are given a Gromov-Hausdorff distance, and the outcome, has the chain complex has the given metric by you. Okay, but the constructing metrics is a challenging for us at the moment.
And yeah. I know there's this one paper by Michael Lesnick, where he writes about also metrics in a homotopy setting. But to be honest, I have not read this paper yet. But does it connect to what he's doing? Do you know? Do you know the paper?
No. We know. We wanted to. Actually, I haven't read it in detail either. So I must confess. So yes, we wanted to study that and to compare and try to come out. Yeah, as Wojciech pointed out, the problem is come out with meaningful metrics on the space we are interested in. So that's it.
So I would like to make a comment again about the paper. So remember, Lesnick's paper, which is very nice, with Andrew Bloomberg, is about metrics on homotopy types. Minimal cover is an invariant, not of homotopy type, but of isomorphism type.
Yes.
Okay, it picks up information about how contractible spaces are. So so of course our invariant are stable with respect to the Lesnick's and Bloomberg metrics, but you forget too much information. This is like just forgetting too much. Okay, we need metrics which are not of homotopy type but more of isomorphism type.
So let me interrupt with two things. I think Sarah, I believe, was asking a question. So Sarah, take it away. And then Barbara, if you don't mind, while doing that, we had a request to post the link to the database in the chat window. So,
oh yes, absolutely.
Or if you could maybe move to that slide, or just chat it in yourself.
Yes.
Go ahead, Sarah.
Absolutely.
I think you had a question.
Okay. Yes. Thank you, Barbara, for your talk. It was very, very nice and very clear. Although I'm not very into model category. So it was the first time I've listened to them, and I have only a question. Maybe it's not so relevant, but if you can go back, please, to where you explained the example of commutative ladders as parametrized tame chain complexes, because I don't. Yes, because as far as I understood, in our setting, we have in vertical chain complexes, and then horizontally radius. Okay. But I cannot see how density can replace boundary maps. I don't know anything.
Oh, no, sorry. No. It was misleading. So the density is just telling me that I have one filtered chain complex, which is changing. So I'm adding more points, okay? And then once I have the two of them, I totally forgot that they are coming from different densities. And I'm just taking H0 of this one and H0 of this one. So the boundary, the boundary is simply the induced map between the two H0s, parametrized persistent modules. Sorry.
We are.
So it's not given by the density.
So we are kind of outside the category of tame parametrized chain complexes.
No. Sorry, no. We are in, because if you have, so this is non-zero just in 1 degree. So this is one boundary matrix, one boundary map. Okay. So it's between. So it's, you can consider this as degree 1, and let me actually show you. So here, okay, I don't have the map, but at least I have the example. Okay, so this is referring to the lower density one, and this is referring to the higher density one. Okay. Okay. So I have just one map.
It's a very special case where I have only one step. Okay.
Exactly. So this is clear. I mean, this is immediately a boundary map because this one is 0, and
there's nothing to show. Okay.
So yeah. No, it's a very special case. So if you want actually to compare 3 density, then is getting harder because you need to work to be sure that the composition is 0. So we will need to.
Thank you very much, because it was very clear to me how to fit persistent modules into it, but not with okay.
Yeah, since you have just one map, you're sure it can be. It can pretend to be a boundary one.
Okay. Thanks.
You're welcome.
Further questions?
I could ask another question if that's okay.
Let me see. Leonid typed a question. Let me see if I can.
Oh, it's a very long one. Okay.
And then we'll go to you, Pipine.
Yeah, sure.
Okay, so let's say I treat the less dense one as a subsample of the more dense one. Yes. Then each one decomposing into minimal interval spheres. No. Then I'm taking both of them as one chunk. So I'm taking the. Okay. So this is the less dense one mapping into the more dense one. Okay. And this is so. Actually, this is the H0 of the less dense one, and this is H0 of the more dense one. Okay, and I'm considering the map between them, and then I obtain a commutative ladder. And then, since a commutative ladder, it is one tame parametrized chain complex, I can compute the minimal cover of the whole of it. Sorry, which is these things here. Okay, so it's one giant thing. And then this is the one that I decompose. Okay, because here now I didn't write the map, but there is hope for this one to be monomorphic, since this space has so this is dimension 3 and this is dimension 5. I can at least hope that I have a monomorphism. Okay. Then to intermediate between the terms of the two decomposition. No, so it is one decomposition. It is the 2 degree of the decomposition. Okay, when the degree 0 refer to something that is happening in this higher density, and the degree 1 is telling me what's happening in the lower density.
Pepijn?
Yeah, so if I understand correctly, the way you treat these commutative letters is you take them as sort of trivial chain complexes in the lowest degrees, and then take a minimal cover of this, right?
Why trivial?
One step,
so
he means.
Yeah, it's sort of one step.
Oh, yes, yes. Sorry, I was thinking about degree below, so I was confused.
So they're only concentrated in degree 0 and 1.
Exactly.
And then you take a minimal cover of this thing.
Exactly.
And use the decomposition as a. What if we do it differently? What if we take just the maps on chain complexes? So from both of these things, as sort of a 2-dimensional persistence module.
Okay.
And that's already cofibrant itself, I would say. Because
well, the point is that then you're moving, is like you're telling me you have 2 grids, right?
Yes.
So, okay, then it means that you're moving 1 dimension up. So I know for sure there exists a minimal cover, but I'm not sure how to decompose it. I'm not sure. So I don't have a decomposition theorem when I move 1 parameter up.
Yeah, right. So that's also what I asked Wojciech, I think, last week. That then it becomes,
so it's something.
So that's already hopeless in there.
Well, I don't know if it's hopeless under any hypothesis. So maybe there is some reasonable hypothesis under which you can find some decomposition.
Yeah, I thought maybe you can in some way recover the rank invariant, but maybe then need a different model structure, or.
Yeah, exactly. So, so what we know is that for sure it exists a minimal cover. How to decompose it, how to compute it, how to compute it we sort of know because the proof is constructive. But what is the information, how to decompose it, how to put it into a diagram, for example, this is another story. Yeah, so it's worth studying. I think it's interesting. It's another direction in which we can go, but I don't have any answer for now. No.
All right, thanks.
So let me take the moment to thank everybody for showing up and for the great questions. I'll stop the recording now, but please stick around if you have further questions, so long as Barbara can stay. So thanks again, Barbara, for the fantastic talk, and thanks everybody for joining in. And please do stick around to ask further questions.